It's up to you, though.
Recording in progress. Okay, I'll start. All right. Right. We went through a lot of stuff last week, and let's see, what do I have? My mm, oh gee, let me get rid of this. Mm, okay. Um, okay, and let's see if I can. No, I don't want that. Yeah. Okay. Okay. If I'm screen sharing, why am I showing up here? And the thing I'm trying to share is, yeah.
Yeah, you're showing the Frank and Ernest.
Okay, yeah, that's okay. They were having a sale,
Yeah.
and oh boy, where and it went away. Oh, here it is. Okay. Mm. Okay, is there a way of getting rid of my oh, it's in the view, isn't it? So I all I see is me. Oh, hide self view. Okay. And I still see myself. Are you looking at the Frank and Ernest thing?
I'm looking right at you.
Oh my, I'm not that glamorous. Uh, okay, I'll try sharing again. And Frank and Ernest. Okay, there's Frank and Ernest. Okay, as we're talking about the basic atom, the planetary style, which is obsolete, but it's good for our purposes. We can still predict from it. So an atom has protons and other stuff in there. The proton is the only thing that counts because it has a positive charge. Electrons have a negative charge. So they're in balance when the electrons are whirling around the protons, equal to number, well, whatever the number is that's in balance. Some some elements will easily shed electrons, and these electrons are basis for our electronics, and they jump from atom to atom, and some things like copper, silver, aluminum, gold, and they conduct electrical current flow. Other things don't, like rubber. People to a certain respect, but these things are called insulators. And a little later on, we're going to get into semiconductors, which are conductors and insulators at the same time. All right. Um, we also talked about. All right, stop share, and here's my and oh geez, I'm locked out of the thing. Hang on. Um, there's, I hope. Oh, wow. Hang on, I have to find another way of getting into my. I've been locked out of that particular thing. Where's okay. Okay, Ace is coming in. And get back and share. And everybody see the display here?
Yep.
Yes, sir.
Okay, so I'm sorry, things don't seem to be working that well right now. Uh, okay, we found that there are two ways of conducting electricity. Of no, creating electron flow. One is by using batteries. And one way is by using a magnetic field. And when you have electrons conducting through a battery, creates a magnetic field, which you can detect with a compass. Oh, and you can also, let's see, where's my, either with, you can use a battery or you can use an alternating current out of the wall. And this coil also creates a magnetic field, but you can see it goes back and forth, back and forth. Okay, so we have alternating currents, which I think I mentioned last week. It's a little more efficient to transmit long distances because you can get the same amount of power or wattage by using a very high voltage and very low current, where if you use direct current, uh, the the uh, the wires act as a sort of resistor if they're long enough, so you have a lot more loss. Okay. And of course, the other thing that I mentioned, why we have these sine waves coming out of the wall, because it goes round and round like a circle. So you have what amounts to a sine wave. If you wanted to put it on a scope, and you'll see a sine wave. Now nowadays, no, back in the day, we used a lot more transformers. We have a transformer. Yeah, here we go.
Can I interrupt for a second?
Sure.
All I see is Jerry. I don't see. Is there a slideshow you're showing or something? Because I don't see anything but
Oh,
you. Did I click on something I shouldn't have here?
Yeah, I see it on my screen.
Okay, well, let me try it again.
If anybody knows what the trick is, let me know.
Yeah, it
And
was it was on my screen, but now it's not. Now I'm in gallery view. Okay, now it's
okay,
back.
there it is. I see it.
Okay, okay. Now, again, I could talk for a couple of hours on this sort of stuff, but we're doing the mile wide and inch deep version of this things to get you through the exam. So anyway, what happens, the magnetic field can transfer power, transfer energy. It can cause the electron flow here to create a magnetic field, which is picked up. The magnetic field is picked up by another loop like this, and also creates an electron flow, as you can see. Now, if you have more, well, you can see the number of turns on this thing. There's a certain ratio. We have 4 turns here. We have 2 turns here. Uh, what we're doing here is stepping down. We have 10 volts here. This will probably make 5 volts. Let's see, got a meter that I can show. No, it doesn't show any. Um, doesn't really show the voltage. But anyway, if you have a primary, the one that's actually attached to the power source, and if it has 100 turns of wire, and you have a coil that's not attached to it that has 10 turns of wire, you're going to have a 10-to-1 ratio. It's going to drop down. So from 100 volts, it'll drop down to 10 volts. Or you can do it like in the old days when I had my 1500-volt power supply. I had a smaller number of turns on the primary attached to the wall, and a lot more turns on the secondary, which boosted it up to 1500 volts. Okay, that clear? All right, I hear crickets, so I guess it's clear. All right, we started getting into components a little bit, and
Yeah, I had a question.
sure,
Are those conductors, the coils, are those considered inductors?
those are considered inductors. They do their job in the magnetic field. We talked about electromagnetic fields. Like the radio wave is a combination of electrical and magnetic. We have components like the coils that operate in the magnetic field, and we have components like the resistors and capacitors, which operate in the electronic field or the electro field. Okay, all right. What happened to?
Okay,
Okay, now what happened to my? All right, try it again. Um, all right, here we go. All right, everyone see the book?
Yes,
Yes,
yes.
sir.
yes.
All right, so we have, okay, talked about the electrical components, conductive surfaces separated by an insulator. That's you can make your own capacitor by taking 2 sheets of tin foil and say or aluminum foil and a sheet of wax paper and wind it up tightly, and it will store electricity. It'll store in the electrical field. One of the questions they're going to ask you, uh, let's see. Okay. Okay, here are various types of capacitors. This one here, can you see my cursor here?
Yes, we can.
Okay, all right. These are in various sizes. The bigger they are, the more likely they're going to be in power supply types of things. Anyway, sometimes it takes a little while for the electrical charge to build up, for this thing to fill up. It's almost like a reservoir. If the capacitor is big enough, you can sort of use it as a little battery. It's kind of strange that way. But if you put an ohm meter on one of these things, now the ohm meter is a small circuit that's uh, you have a couple of uh, known components, the values of the known components, and so the meter will show you the value of the unknown component. In this case, the value of the capacitor or the value of the resistor. The capacitor will try to steal electricity from the ohm meter to build up a charge. So what you'll see in the meter is that you'll first find almost 0 ohms. It'll dip down real fast, and then later on, it will you'll see the meter sort of build up to a high resistance, and that's normal. And I'm only mentioning it because that's one of the questions on the exam. Okay, we talked about the coils with their types of building up the magnetic field, and when the magnetic field collapses, it turns into and induces electronic flow in the coil.
I have a question.
Sure.
Is there a way to identify a capacitor by like the numbers or letters on the outside
Yeah.
of like the writing?
You're not going to see it very much anymore. Let's see if I can get this thing. Well, if you have a manual, you could probably look at it a little more. They used to have color codes for both resistors and capacitors, and you could tell. There are charts.
I know
Uh,
the capacitors one is still in use as much as I've seen, even with like small microelectronics, like that you have to see with a microscope. Capacitors, I haven't seen it as much though nowadays.
right. Resistors have the stripes. Capacitors used to have sometimes stripes, sometimes little dabs, and even diodes would have a color coded themselves. But at this point, you're going to just see something in here that will give you the 3 things. Number one, the value of the capacitance. Number two, the voltage rating of the capacitor. And number three, the tolerance, how close to the stated value it is. Now, something like this, which is what, 470 microfarads, it's not going to be very precise. You might get, see, a 10%, plus or minus 10% on that. And some of the others are a little more precise. You have some that are in the picofarad range, and those have to be quite a bit more accurate if you're designing a circuit. Okay, we talked about another little thing. Capacitors will not pass direct current. They just don't. But they will allow alternating current to go through. Okay. And that's called resistance. Inductors will pass direct current. Physically, there's no reason why they shouldn't because they're wires. However, if you try to put an alternating current through, it's going to start resisting the flow of current that way, and that's a good thing. This item itself was used in tube circuits. I guess they're using them still in transistor and chips. But what this does, this will allow direct current power supply for the power supply to go to your transistor. But if the transistor is putting out, say, a radio frequency signal, it will now not allow the radio frequency signal to go back through into the power supply. That's called a choke. Okay. Talked about adjustable things, potentiometers for resistors, a variable and capacitors. This one looks like a little egg slicer. This one is actually two pieces of metal that are separated by a very thin layer of rock, mica mineral, and that's the insulator. And there's a little screw in there that you can adjust the distance between the two to adjust the value of the capacitance. Okay, we talked about transformers just now, transferring energy from one place to the other. All right, now, if we're going to talk about radio frequency, audio frequencies, things of that sort, the coils and capacitors, the inductors and capacitors, are also going to be showing some kind of resistance to the flow of some of the current. As I said, the inductor is going to resist the flow of alternating current. Actually, it's both the inductor and the capacitor will resist the flow of radio frequency current or audio frequency current. However, the capacitor will resist in a negative way and the inductor will resist in a positive way. At a certain frequency, the positive resistance and the negative resistance will cancel each other out. And the combination of a capacitor and an inductor will, at that point, is seen to be in resonance. Okay, that's okay. They're talking phase differences. You don't have to worry about phase differences, but anyway, the opposition is called reactance, capacitive reactance, and inductive reactance. When the capacitive reactance and inductive reactance at a certain frequency goes to a fairly low value, like 0, the circuit is in resonance, and you can use that. For instance, I have a beam antenna. Let's see if I can. Oh, not that one. Okay, I'll stop sharing for a second. And let's see, where's the white? Um, uh, okay, I'm going to need a little help on this. Where's the whiteboard?
It should be under lower right hand corner. There's like a circle with three dots that says more. If you click on that, I think the whiteboard application should come up from there. I think.
Except I don't see it on here. Wait, let me get this out.
Yeah,
Share,
she's right. It's if you see the share button, go about 4 buttons over.
let me try that again. Okay, share. 1, 2, 3, 4. More.
And more. Yeah, click on that.
Okay, new whiteboard. And okay, it says hola. And can you see the whiteboard?
Yes.
Okay, all right. I have an antenna. I no, blah, 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 blah. Clear page. Okay. Okay. I have an antenna. It's one of the elements of my Yagi beam antenna, and it's supposed to be uh, no, it's the and a sec interference from one of my programs, and I'm trying to close it out. Okay, everybody here? Okay,
Yes, sir.
all right. This the inductive reactance and the capacitive reactance are close to zero at a certain frequency. Let's call it 14 megahertz. Now, I want to operate this on two other frequencies. So what I can do, I have terrible handwriting on a mouse. What can I say? I can hook up a circuit of an inductor and a capacitor, and this is a series circuit, right? Anybody there? Bob?
Yes, sir.
Okay,
We're
Rick.
here.
Rick, is
We're
this
all here.
are these two components in series? You're shaking your head, and you're right. They're parallel. Now, the interesting thing here is that a parallel circuit creates a great amount of impedance. So it sort of blocks. So if I put that circuit, I cut this and put that circuit in there and there. And I have this, the component set to block at 21 megahertz. What I'm doing is electronically cutting the antenna to a different length so it will be resonant at 21 megahertz. And I can put another one of these circuits in. So it will cut the antenna wire short at 28 megahertz. So I have one piece of wire for these circuits, and I can operate on 14, 21, and 28 megahertz with the same antenna. That is called a tri-bander. And when people start talking about tri-band antennas, now you know what it is. And there's some other antennas that are, well, we'll talk about that later on.
Does those megahertz that you just mentioned have any relevance, or is it just random numbers you chose?
No, 14 megahertz is the 20 meter amateur radio band. 21 is the 15 meter band, and 28 is the 10 meter band. There are a couple of things get a little more complicated. There are a couple other bands that the FCC gave us. It's 18 megahertz and 24 megahertz. And sometimes it's difficult to make these circuits. These circuits are also called traps. Sometimes difficult to design something. Some people will just make a separate antenna for those two frequencies. They were given to us recently. Some of the old equipment does not doesn't have the circuitry to cover those. Okay. All right. Okay. And did I stop sharing? Yeah, I guess so. All right.
Yes.
Okay. So much more stuff we have to. Okay. All right. Share. And okay. Now you're going to see in a lot of equipment and antennas the impedance of 50 ohms. Most of the radio transceivers are built to see an impedance of 50 ohms from the antenna.
Is there any reason for it being 50 ohms specifically?
I think that was actually I'm trying to think 72 would be better because 50 ohms is the natural impedance of a dipole. That's cut to resonance at any frequency you want. But they use 50 ohms, and the antenna is not at the resonant frequency. It's going to have a much different impedance. And the difference between, well, we'll get, when we talk antennas and stuff, we'll get into SWRs and stuff. But this mismatch will make the transistors that are pushing out the power from your transmitter very unhappy. And it's not like the old days where they had tubes could take a lot of abuse. Transistor does not take abuse; it dies. So we have to have workarounds, which are called antenna tuners. And what they do, they deceive the transmitter into thinking that it's getting 50 ohms impedance, even when it's not. So anyway, that's for another day.
No offense. What is a dipole? You lost me at the start of that sentence.
Okay, a dipole is a okay. Let me get the whiteboard again. Uh,
Sorry to keep you making you go back and forth. I'm just trying to pay attention.
oh, you should feel very, very bad about this. You're making me do my job. What's wrong with that? Okay, all right. Let's. Okay, a dipole is a wire that is in two sections.
Is it similar to like tripole you mentioned?
No, no, tri-band is a different concept. Dipole.
Ah, shoot.
Okay. And anyway, again, it's not within your pay grade at this point. But the wavelength here's a half wave, here's a full wave. The wavelength of an antenna. It seems that we transmit on a half wave antenna. A dipole is a half wave wire that cut in half that is one half wavelength long. Um,
And it's die because it's two die.
right. Okay. And it's fed to the transmitter with two wires. Now it could be uh, a ladder line, which we'll show you later on, which is looks like a ladder of two conductors, or it could be something that's more familiar to you as oops. Huh. Where's my here it is. It could be the coaxial cable where the center goes to one of the one half of the dipole, and the braid on the outside goes to the other part of the dipole. And so anyway, that's the dipole, and that works for just about everything. When we talk about the three-element Yagi, only one of the elements is actually fed uh, down to the transmitter, and the power from this dipole, it's called the driven element. It will go to one of the elements is a little longer. No, it's not attached to anything. It's called a parasitic element because it's sort of depends on the power. It's a little longer, and it will reflect. It'll keep the power from going in the back. And the next element, called the director, is a little shorter than the driven element, and that directs it. So what you're going to have is a very directional antenna. And that's why they're very popular if you can afford them. After 60 odd years, I have a three elements tri-bander Yagi antenna that's mounted up around 34 feet high, and it's getting me around the world. All right, again, with antennas and stuff, that's really next week's test propagation. Okay, does that answer your question, Ace?
Somewhat. Is it so that curve is the sine wave, correct?
Yes.
We're putting elements in between at different points, kind of like a alternator would with like the oh, what are they called? The 3 points of an alternator to receive that sine wave
Well,
of electricity. I
except
think.
two of those three poles aren't connected to anything. Where the with an alternator, all those poles are connected to the power. So these are parasitic. They depend on whatever power is being generated through the driven element. Okay, so anyway,
I think I follow.
okay, good. Okay, so what I was just trying to say is at resonance, you can either use, oh, Mike is holding out his driven element there. Okay,
Dual band dipole,
dual band dipole.
2 meters, 70 centimeter.
Okay, and 2 meters. Let's see, quarter wave is what? No, half wave. It's about 36 inches.
It is.
36 or 38.
It
Yeah, 30,
is
39 inches is a half, and so
Mhm.
a quarter wave would be
19.
19 inches.
Yep, I just measured. It's 19 inches.
Yeah, and the 440, it's what, 6 or 7?
Yeah, something like that. Let's see here. It is about 5 3/4.
We got charts and formulas. We have
Yeah,
charts.
yeah. There's real measurements to make them, more than just what I just gave you. But
Yeah.
it's someplace around there.
Okay.
But you were talking about you know um, Yagis and the affording of buying, and I'm one of those guys that I don't want to spend the money on it. I want to make it, and so you can make your antennas.
Yeah.
I have a lot of fun with that. That dipole that I held up, that's one that I made.
Hmm. Yeah. Well, for instance, I have a fancy antenna before I could afford the tri-bander. I used a staple gun and wires and some of this ladder line to make a directional antenna up in my attic. And just stapled the stuff to the boards up there, and it worked pretty good.
Mhm.
Great. Any other questions on that? All right, I'm going to get out of this.
While you're getting back out of this, Jerry, just one thing to add in with your question about why 50 ohms, Ace. Um, um, all the radios that we use want 50 ohms. So that's why you want your antenna to be, your line to your antenna and your antenna to be in resonant with 50 ohms.
Is there any reason the radios were originally set up with 50 ohms?
They weren't. Back in the day, they were using tubes. They were using sometimes random lengths of wire. I know I used to convert war surplus. Oh, okay, here's Larry coming in. I used to buy some war surplus gear and convert it to ham use. And some of these things, like a tank transmitter, the tank could not put out a 64-foot long dipole for its antenna. It used a a 10-foot whip or something of that sort. So the impedance of that was just horrible, just very, very, very low. So the output circuitry for those was designed for very low impedance antennas.
Video the other day asking people. I made a video.
Hello? Okay. I like this. I don't know if you're seeing this on the whiteboard. There's I don't know if it's a screensaver type thing, but the names of the class participants are floating across the whiteboard. This is something only I can see.
No, if you move your cursor around, you see my cursor in the center of the screen.
Oh, okay. So
I can actually
Wow.
draw on your whiteboard. I found out accidentally a little while ago.
okay.
I grabbed my
Yeah,
cursor
I
and
found
moved
out
it,
I
and I
can
made a little
erase
line
on.
and went, "Oh my gosh, did I just do that? Whoops!"
Yeah, I found out I can erase on his whiteboard. So
Okay, so this is a kind of my son was sending me all these little fidget tools for my keychain, so I guess this is another outlet. Okay, all right, let's get out of that whiteboard. Now get back to the book. All right. So, which of the following is combined with an inductor to make a resonance circuit? An inductor and a transistor. Yeah?
no,
What?
an inductor and a capacitor.
You got it. Okay, and of course the book's going to have right here. Circuits that contain both a capacitor and inductor are called resonant circuits or tuned circuits. I showed you one of the applications.
Some people call them tank circuits too.
Especially when they're outputting the amplifier, the final amplifier of the transmitter. And that tank transmitter of mine, oh, I'll get a picture of that sometime. There were some parts of it, the interior, where it looked as if it was big enough for Ginger Rogers and Fred Astaire to do a dance. It was big enough. And the doggone thing was big enough sturdy enough to sustain a couple of 50 caliber machine gun bursts. It still work. Anyway, all right. One other thing. If a tuned circuit is in series, it will pass a certain frequency through. Now, if you put that tuned circuit, say, on your receiving antenna and make it go to ground, like here in Oak Park, I'm at this is the outskirts of town. There were farms out here when the radio stations came in, the TV stations came in, and so no one believed that there'd be housing developments and a lot of people living out here. Well, we're here, and if I turn on my FM radio, I can hear some stations at 5 or 6 points on the dial because I'm getting overloaded. So if I have a particular radio station that's bothering me, I can make up a little tune circuit and have it only that one frequency pass down to the ground so it doesn't bother me and it won't bother the radio. So that's one good thing. And also back in the day, you don't have to worry about neighbors' TVs dancing up and down as much when you're operating. But we did, and we had these high pass filters which we'd put on the TV set, which would pass the TV signals, the high signals out, and ignore the ham signals, the lower frequencies. And we also have low pass filters on the transmitters, which would pass our low frequency circuits, our low frequency signals, and try to reject the high frequencies that would go into the TV sets. It was kind of bad because the TV sets. Well, first of all, TV channel 2 was at 54 megahertz, and if you were operating on 10 meters, which was 28 megahertz, which no, 56 is the third harmonic of 28. Brooke, you're thinking. You're right. It's a second harmonic. Anyway, and TV sets weren't built with very much precision, and they would pick up our signals very easily. So we had to buy all these filters and things of that sort, or else the neighbors would go on the warpath. Okay. All right. Um, where's okay. All right. These little insects, which weren't around until the 1950s, and they pretty much replaced tubes, except in high power things. And diodes, well, you can see these. These are very heavily built, and they're actually designed to go on large pieces of metal that will absorb the heat that this thing generates. They're called heat sinks. The diode is the semiconductor that I was talking about, where it'll only let current pass in one direction. So if you have, well, uh, let's see, where did I put that? Um, Hang on, I'm going to turn this off for a second. No, it didn't work. Okay. Okay. When you get your Harbor Freight meter, you can do things like this. Or if you want to buy a nice fluke meter, the fluke is pretty much the Mercedes of test instruments. Okay, where to go? Okay,
Harbor Freight is the way to go.
everyone see the display here?
Yes,
Okay.
but $529, I don't think I'll get one.
Uh, not to start. No,
I think that's a fluke.
if you can start designing your own circuits after a while, then might be a good idea. But anyway, and of course, if you're in a business, your tools make you money, so it's good to have something nice like that. Okay, so one of the things you can do with a meter, if you put your meter contacts on the diode in one direction, it acts as a switch. It will flow from the positive lead to the negative. Or if you flip the contacts around, it'll act as a big resistor. So a good diode, if it's hooked up like this, it'll show 0 ohms or a very low value of resistance. And if you put it on the other direction, oh, bad diode. Oh, come on. Where's the other good diode? It's going to show 0 ohms. And then if you put it on the other side, it's going to show some thousands of ohms as acts as a resistor. Okay, let's go back to um, where's the oh here's hmm, okay, I guess we don't have the circuits. All right. Anyway, one other thing that a diode will do, it will separate out a mixture of signals. For instance, if you have I don't know if anyone remembers crystal radios. Nobody?
I
I
remember
remember
when my
here,
dad used to buy crystals for a police scanner. I don't know about crystal radios.
No, that was the crystal was used for a different reason, for as an oscillator to reach a certain frequency. But uh, you could use a rusty razor blade. It would act as a semiconductor, and it would take radio signals off your antenna and separate out the radio signals. That it would treat that as an alternating current. And if there was a voice or music attached, it would sort of set up a pulsing according to the sound, and you could hear that on your headphones. A basic crystal radio set consisted of two things: on a Quaker Oats box and a cream of wheats box with wires wound around it. The and that would and then that would be attached to an antenna, maybe 50 or 100 feet of wire that would pick up the radio signal. The two coils on those two boxes would act as a transformer, and then the transformer would go to the diode. The diode would do its job, making this pulsating direct current, which would pulse the earphone so you could hear things. So that, all right, let's see anything else. Okay. All right, we're back to the diodes. Now, diodes were in use from the early days. Uh, one of the early pioneers actually used some contacts dipped in acid. Kind of hard to put that in your pocket and walk around with it, but it made a very nice detector for radio waves.
Okay, we're still seeing the fluke
You are okay. I'll stop.
multi-purpose things. There you go.
Okay, and I'll start. And okay, got it.
There we go.
Okay,
We're back to the diodes and transistors.
okay, and they're used for just about everything now. As I said, so some of these are built very heavy duty, and they're meant to be screwed into a piece of metal that will lead off the heat that they generate. Now, something like this you'd find in some power supplies or audio amplifiers or things of that sort. This too is something like that. Uh, they can they can be triggered. Uh, you can see that let's see. Some of the diodes have separate leads. If you put a voltage on, it will act as a big switch, and you can turn it on, and then you have to cut off the power to turn it off. Those are oh, brain burp. Uh, it'll come to you. Anyway, diode is a slab of silicon which has a couple of impurities, uh, little pools of impurities in there, which the leads are turned to. And when it's made like that, it will either pass or reject. It'll act as a semiconductor. Transistors are a little different. They still have the slab of silicon or various other materials as the chemists and physicists find it. They also have a third little deposit of impurity, and that acts as a base or a gate. And what that does, let's see, uh, I thought I had, that. Hang on, I'm going to stop share. I'm going to go into something else. Um, okay, I'm going to share this.
Yep, we see it.
Okay, this is a power supply. You have a certain number of diodes in here. Three of them, as a matter of fact. And here are three of the purposes. This is the diode that converts the alternating current into direct current. Now we have the sine wave here. The diode will only let the positive part of the sine wave come through. So you're going to, instead of having this like that, it's going to go this, a space where the other part of the wave is supposed to be, and then another hump, and another hump, and another hump. Doesn't help us too much. However, that's where the capacitor comes to the rescue, because the capacitor, when it gets the positive hump, will charge up, and when there's a negative hump or a negative flow, it will push up and make it a little straighter. So it fills the gap. Okay. This is called a light emitting diode, and it's not our pay grade to start thinking about what kind of light does it emit? Is it emitting waves, or is photons, particles, or waves? Anyway, it makes light. There is an equivalent type of semiconductor. Uh, you can call it a photocell or whatever, which can take light and turn it into uh, electrical conductivity. So you can actually build a transmitter that's, you can add your voice to the light and send it out, and someone on the other end can pick up the light and translate it back into sound. Anyway, this is a good indicator for things. It is a diode, though it can work in certain circuits for you, as well as emitting light. This one, you can see from the way the anode is set up. This is called a Zener diode. It comes in various configurations, voltage configurations. There's some that are set for 5 volts, others for 12 or 14 volts, and others for 24 volts. And what happens doesn't do anything unless the voltage exceeds what their rating is. So if this is set for 5 volts and we have a 5-volt power supply, if something happens and goes up to 5.5 or 6 volts, this thing is going to act as a resistor, and it's going to try to bring down the voltage back to the 5 volts. So Zener diode, that's a very good thing. Okay. While we're at it,
Is that switch pretty common in power supplies like this?
which?
The number 3, the switch.
Oh yeah, it's universal.
Correct.
Okay. You can see well, switches are everywhere, and
Like switches are common, but in my most of taking apart power supplies nowadays, I mean, you plug them in and they're going to put out a power supply. Does it like usually triggered by like a demand for power or
well, right, so they can get more sophisticated, but no, this is a basic, and there are things that are missing that you'd put into a power supply design. But again, this is the basic. This is called a single pole. It works on one conductor, and it's a single throw. It only goes on or off. Sometimes there's a choice. There's a pole here and a pole here, so it can turn on 2 circuits. Actually, if you live in a house that has stairs, there are usually 2 switches, one at the top of the stairs and one at the bottom of the stairs. And it's set up with 2 poles. So you can, if you're at the top or the bottom, you can either turn the light on or off. That would be a double throw. And they have more complicated switches, three or four different that control three or four different circuits. So this is the basic single pole, single throw. This is a standard United States plug or socket. This would be the plug. The small contact is the hot one. And that's also black wire. If you open up uh, your wall plate, you'll see a black wire, a white wire, and either a green or a bare wire. The white wire is the common or neutral, and the green wire or bare wire is ground. You can see this little fork type thing. It means the chassis ground. You see it all around here. It's all grounded to the chassis or to a common wire. And fuses. Well, what do we know about fuses? I remember when I was a kid, so someone was bragging about they don't have to buy any fuses anymore. They just unscrew the fuse, put a penny in it, screw the fuse in, and there you go.
Fuses limit the amount of current that can pass through. They oftentimes have limitations on the amount of voltage as well, but current is the bigger factor. At a certain amount of current, they'll break or melt through, depending on what materials are in them.
Absolutely. So it's false economy. But no, a lot of a fuse is something that has a wire in it that will melt if it reaches a certain temperature. A certain amount of current goes through, it reaches that temperature. You can see them. There's cylindrical fuses, or the automotive type fuses with little blades, but you can see the little loop of wire, and you can see whether or not the fuse has been melted or not. When a fuse goes, it goes. If you have a circuit breaker, it's kind of a switch that operates on high temperature, but once it cools down, you can reset it and use it over. So it costs a lot more initially, but it's worth it. Okay. Any other things that we haven't? No. Okay. All right. This thing seems to have killed itself. I'll have to pick that up another time. Okay. This is a common antenna tuner. As I was saying, it's supposed to make the transmitter happy if the antenna doesn't match. And it uses a combination of capacitors and an inductor. You can see this arrow, which means it's variable. So manipulating this, I have one for a wire that I've got. By manipulating it, it gets the signal out and keeps the transmitter happy because it believes that it's working into a perfect load, a perfect antenna. So actually, one of the things I'm doing now, I was introduced at the beginning of the month to one of the digital modes called FT8, and it's designed for very, very low quality signals, very signals that are in the noise and all that. And this software for the FT8 program is very sensitive and can pick it up. So you don't need as much of an antenna. or as high a power as used to have in the old days. And I'll tell you, I'm getting stations that I haven't contacted in 60 years. Like I've never gotten India. I've gotten about 4 Indian stations. New Zealand and Australia are coming in like gangbusters. Uh, if there's some time in the coming weeks, I'd like to show you a little bit about the software that I use to control my transmitter. And it also has access to a bunch of remote stations around the world, and it'll tell whether it has heard my signal. So I'm astounded at what science has done so far. Okay, all right, and here I am again. All right, any questions? Okay. Uh, the one thing that, let's see. Um, okay, right back to this. By this time, you should be starting to go through the online exams. As I say, the ARRL has a free question exam, and what you can do, you can pick the chapters that you want to be tested on, and ARRL will give you exams on just those questions. And of course, by the time you've advanced a little more, you'll start taking the complete exams and take as many as you can until you can consistently get 85%. So let's see. Okay. ARRL.org exam review. That's in your manual, and it's in your Kindle. I'm using the Kindle on this right now because I had the kids here and they wanted to clean up the house for me, so now I can't find anything. But I couldn't find my physical copy of the manual. Yeah. Anyway, all right. Okay. One thing, mea culpa, I have not gone through all of the exams with you. I hope you'll forgive me. I'm actually laying that on to you. And circuits. All right, they talked about frequency, phase modulation, bandwidth, sideband. Do we need a little review of that? Anybody?
It wouldn't hurt.
What's that?
It wouldn't hurt to just do a quick review.
Wouldn't hurt. Okay. All right. Okay. Talked about fundamental waves and harmonics. And we use filters to filter out the harmonics. We're enjoined by the FCC rules not to put out a pure signal, to try to reject any of the harmonics that might interfere with someone else. Okay, now Okay. How a receiver sees the radio spectrum. Um, okay. They're starting off with the AM radio band. And you can see it comes up. There's a sort of peak and a little curve there. And amplitude modulation means that that uses the up and down, the power of the signal as it goes up and down. Uh, when you're attaching the voice to it, then that's what you get, the amplitude. Okay, let's okay. Um, let me get out of this and get into something else. Um,
Well, Jerry,
yeah.
can we, where were we? You see my screen?
Hang on. I was looking in the. Yeah.
Okay. Now you took them through some of these symbols, the chassis ground and the earth ground,
Yeah.
but I wonder if we should take them through some of the special grounding um, situations. Like because see, there's the earth ground you saw in the chassis ground, but sometimes if you're up high, you need the high ground, which looks like that. That's a symbol for the high ground.
Yes.
And
Yes.
and if you're not sure that that's the right thing to do, then you can always take the moral high ground.
Yeah.
Okay. But in any case, it should be a stable ground, you know?
And I wore my Dare shirt for this.
Okay.
And
And of course,
and
yeah, of
and
course,
not only should it be a stable ground, but there's also something called a ground wave.
yes.
And but in any case, you should have a really good ground. And that's the symbol for good ground. And or if you need a little better ground, here's the symbol for a little better ground. Ah, yeah, ground chuck.
Oh, okay.
And
Don't show
and
that
then if I
to Corel.
You're killing me. Killing me
okay,
here.
Yeah.
okay, but then you just have to be careful because if you don't ground right, you get something really dangerous. Okay, so this next one is that's a dangerous ground. And yeah, you don't want to fool around with that. So
Oh, yeah. Very good. Very good. Yeah. Yeah. When we get into station construction, I mean, if you really want to get some good grounds, Home Depot or Lowe's can furnish some very good things. I actually have several 8-foot ground rods driven into the ground. They're fed with some like number 6 wire, which is a very, very heavy duty wire. And that's hopefully to divert whatever lightning strikes the tower down to the ground. But I've even seen ground tortured. Gets very spongy if lightning hits it. Okay, let's see where else am
so
I?
you know what, Jerry, I can. you know what we could do in these last few minutes is just run them through the questions. I have I have those all sorted out, if you'd like.
Okay. Uh, okay. First of all, are there any other questions that we haven't gotten through? Any other things that let's see. No, that's not it. Um, okay, that's just gone. Yeah, I think that'd be a pretty good idea.
Okay. Now, let me get there. Okay. All right. Now, I've got these set up so that it's got the answers highlighted. So we can go through these pretty quick, but at least it'll give the people a chance to just make sure they've seen all the questions. And if they need to ask a question about them, please pop up, shout something, and
Yeah,
we'll do
well,
it.
Mike has a philosophy of let's show everybody the right answer. They don't have to start diddling this.
Right. Now, is it on my screen? Am I sharing?
Not yet.
No.
Oh, okay. Let me
Yeah,
try
and,
that again.
and yeah, what Jerry's talking about is not reinforcing wrong answers.
Right, right. Uh, slideshow. No, not that. Uh, slideshow. No, hang on. All right, I'm not sharing, am I?
Mm,
Nope.
not yet.
Sorry, hang on. Let me get back to. All right, let's try this now. But now,
Yes.
Yep.
okay. Yeah, now, okay, and it's you can see the first question.
Yes.
Okay,
Yes.
electrical current is measured. All right, yeah, we're just going to run through this real quick. There's a bunch of them, but you guys, if you've got a question on these, if these don't make sense, shout something, and Jerry will explain it to you.
Well, to the best of my ability.
Okay. All right. Electrical units are measured in amperes. Electrical current, right? Um, the flow of electrons. What's the name for flow of electrons? The flow of electrons is current. Okay. All right. The electrical term for the force that causes the electron to flow, that's voltage. Also sometimes called electromotive force. It's abbreviated with the letter E for electromotive force. Okay, which of the following describes alternating current? Current that alternates between the positive and negative directions. All right, these are the actual questions that could appear on your exam. What instrument do you use to measure electric potential? Remember, electromotive potential is the same thing as a volt, so you would use a voltmeter. Okay, and what do you use to measure electric current? Current, that's amperage, right? So you need an ammeter. Okay, here is a nice series circuit. Isn't that pretty? Now, uh, oh, well, there's no questions about that. Okay, and this is a parallel. and the voltage is the same. Um, you know, across all these things, uh, across each of the components. In a series circuit, it's the current or the amperage that's the same in all the components and all the light bulbs. So if the battery is putting out 6 amps, then each of these bulbs will have 6 amps going through it. Okay. All right. What type of circuit is DC current through all the same? What type of circuit is DC current the same through all components? Okay. Current the same. That's series. But if the voltage, if you want a circuit where the voltage is the same across all the components, that's a parallel circuit. Okay. Um, how is a voltmeter connected to a component to measure voltage? It's connected in parallel. And let's see, did that? Okay. So if you wanted to measure the voltage here, you would put another you would connect it on each side of the battery, right? Um, you wouldn't connect it in series like this. You would connect it like this. And so, the next question is probably going to ask you if you want to connect an ammeter to measure current, how do you connect it? Well, the ammeter to measure current, you would connect it in series, just like another one of these bulbs here. Okay. And to measure current in series. All right. And which of the following can damage a multimeter? All right, attempting to measure a voltage using the resistance setting. Okay, if you want to measure voltage, you don't want to set it to measure ohms. Okay. Now, which of the following measurements are made using a multimeter? A multimeter, you can measure um, actually, you can usually measure voltage, resistance, and you can usually with a multimeter also measure current. So volts, ohms, and amps, usually. But the question only gives you two, but voltage and resistance, volts and amps, or volts and ohms in this case. Okay. What reading indicates that an ohm meter is connected across a large discharged capacitor? And that's the resistance will be increasing with time. Remember, when you shut off the power to a capacitor, it still has some charge, but that charge will be bleeding off in time, meaning as the charge bleeds off, the resistance is going to increase. That's right, Jerry, isn't it?
Yes.
Okay.
And
Thank
in
you.
junior high school, we used to charge the capacitors and leave them out for people to touch. We were nasty.
How many times did you have to stay after school for that?
I enjoyed staying after school. We actually had a radio room with somebody
Oh, okay.
with I think the instructor built his own receiver, so it was kind of neat.
Okay, what precautions should be taken for measuring in-current resistance with an ohm meter? Yeah, make sure make sure the circuit's not powered first. All right. What precautions should be taken when measuring high voltages with a voltmeter? The best precaution, have someone else do it. But failing that, just make sure that the voltmeter and the leads are rated for whatever voltages you're set to you're trying to measure. One of our little handheld voltmeters won't necessarily measure really, really high voltages. Okay, what's the unit of electrical resistance? That's ohms. This stuff, are we doing okay, guys?
Yeah.
Okay. What metals are generally good conductors, or why are metals generally good conductors? They have many free electrons, okay, and that lets current go. Which of the following is a good insulator? Well, since all the others, three items on here are metals, and they're going to be conductors. So glass is the insulator, and that's the correct answer. Okay, what formula is used to calculate current? Okay, now Jerry talked about this. You sit down your exam and you draw that circle, you put the line across the circle, E goes on top, and I and R go on the bottom. All right, so to calculate current, it's going to be E divided by R, right? Volts divided by resistance. And how do you measure voltage? All right, voltage is that top number, so you're going to say I times R, which is amps times ohms. And of course, this is the other part. Resistance equals, volts over amps. All right. Now you know what? You can take a calculator into class. You're really not going to need it. What follows is a series of a couple of questions that require really just basic arithmetic. Okay, now you notice that the resistance of a circuit, all right, resistance, what are you going to do? You're going to take volts and divide it by amps. Okay, so 90 divided by 3, that's going to give you 30 ohms as resistance. All right, the resistance for a circuit with the applied voltage of 12 volts and 1.5 amps. All right, you're going to take the 12 volts, again, that's that top number, and divide it by 1.5, and that's going to give you 8 ohms of resistance. And what's the resistance of a circuit that draws 4 amps from a 12-volt source? Again, the voltage you're going to divide by the amperage, okay? 12 volts divided by 4 amps gives you 3 ohms. And this is just another one. You're going to divide volts by the resistance. All right, voltage divided by the resistance of 80 ohms. It's going to give you 1.5 amps. I think we probably had enough of those. Let's move on. There's a bunch of those, but they're all really, really easy.
And that's because they have so many versions of the exam. So they don't want people to look at their neighbors' papers and see something familiar.
Okay, now we're going to move to start talking about power now. And this is that second circle that Jerry told you to draw. You draw that circle, and P goes on top. It's power, which is watts. All right. So electrical power is measured in watts. And what's the term that describes the rate at which electrical energy is being used? That's power, and it's measured in watts. All right. And then we're going to have a bunch of these more simple, real, or very, very simple little arithmetic problems. So how do you calculate electrical power in a circuit? Power, that's the number on top, and you're going to take current, intensité, which is amperes, times volts, all right? Watts equals amps times volts. And that whole thing is going to work just exactly like the whole set of little arithmetic problems we just went through. Okay, so voltage of 3.8 volts and 10 amps is going to give you a power of, 10 times 13.8 or 138 watts. All right, and we've got, and again, there's a series of those real easy little multiplications. How am I doing on time? Oh, I'm doing okay on time. All right, the ability to store energy in an electric field. This is what Jerry was talking about. This is capacitance. All right, this is an easy question. Store energy in an electric field is capacitance. Store energy in a magnetic field, that's inductance. Oh, which is probably the next question. Oh, no. Okay, the unit of capacitance is the farad. And like Jerry told you, 1 farad is that's a very, very large quantity. Okay, the ability to store energy in a magnetic field, that's inductance. Okay, and a unit of inductance is the Henry. Again, named after a guy who, not surprisingly, his name was Henry. All right, the electrical component that opposes the flow of current in a DC circuit, that is a resistor. Actually, a resistor is a name for any component that opposes flow. All right, an adjustable volume control. That's what component is often used as an adjustable volume control? That's a variable resistor, or also called a potentiometer. And old timers will sometimes call those pots. Okay, but potentiometer, variable resistor. Okay, the unit of resistance controlled by a potentiometer. What electrical parameter is controlled by a potentiometer? Resistance, yes, because a potentiometer is a variable resistor. All right, what component stores energy in an electric field? Well, we said capacitance is, or a capacitor stores energy in an electric field. This is just the other side of that question. You could very well get one or the other. If you're lucky, you get both questions, but because it's an easy one. Okay, electrical component consists of which electrical component consists of a conductive surfaces separated by an insulator, and that is a capacitor. And what type of electrical component stores energy in a magnetic field? That is an inductor. What component is typically constructed as a coil? You remember all those pictures of coils or of inductors that Jerry showed you? They all kind of look like they were wound wire, right? So that's what an inductor looks like. It often looks like a coil. And what component changes 120 volts alternating current power to a lower alternating voltage for other uses? And that's a transformer. Okay. And what is a unit of impedance? A unit of impedance is the ohm, just like resistance. Okay. And what is impedance? Impedance is the opposition to alternating current flow, AC current flow. Now, remember, resistance they spoke of as being opposition to direct current flow, but it's kind of the same thing. But impedance is specifically opposition to alternating current. Okay, and which of the following is combined with an inductor to make a resonant circuit? Remember, a resonant circuit's got to have an inductor and a capacitor. Okay, inductor and capacitor. Let's see. Which of the following is a resonant or tuned circuit? And that's an inductor and a capacitor in series or parallel. Could be either, but it has to have an inductor and a capacitor. Okay, and what is true about forward voltage drop in a diode? And that is, it is lower in some diode types than in others. In the book, I forget how much detail they go about talking about the different kinds of diodes, the Zener diodes and the other kinds. Um, but some of them, handle forward voltage drop differently. Okay, so if you see this question, forward voltage drop in a diode, just remember that it's lower in some types than in others.
The common power supply diodes that we use, the 1 in 4,000 series and all that, have something like an 8/10ths of a volts drop. So when you're engineering a power supply circuit, you have to account for that zero point 0.8 volts drop. Some of the more sensitive ones that you use for detecting signals, that's they can be 3/10ths of a volt or less. But that's again beyond our pay grade.
Okay. All right. What electrical component allows current to flow in only one direction? And that's a diode. That's an important thing that a diode does. Okay, and what component can be used as an electronic switch? A transistor. Transistor can be used as a switch. And which of the following components consists of three regions of semiconductor material? And that's what a transistor is. It's three regions of semiconductor material. And what type of transistor has gate, drain, and source? Okay, this is just one of those things you just have to memorize, because I don't know that there's any way to guess it, except, yeah,
Well,
except a Tesla effect, whatever is, I don't think that exists. Um,
bipolar junction is just a generic name for a transistor.
yeah, that's, and, but
Gate,
so
yeah,
a field effect.
yeah, field effect. Okay, great drain and source are the same as well. Gate is the base of a transistor. That's the terminal that gets the small signal or something that controls the flow of current between the drain and the source, or the emitter and collector. The source would be the same as an emitter, drain, same as a collector. But again, they just want an answer for that question, so you don't have to go into all the ins and outs of it.
Okay.
While you're at
And
it, early on, Ace asked a question. Uh, okay, why do we use transformers years ago, but nowadays not as much? Just curious. And my answer was, we still do, but they're smaller. The switching power supplies, which are in the wall warts and the computer power supplies and all that sort of stuff, they raise the alternating current frequency pretty high, which requires less metal and windings, so transformers are small. I have two 20 amp power supplies for my radios. One has a regular transformer and it weighs about 16 pounds. The other, the switching power supply, weighs 2.5 pounds, but has the same capacity. So,
okay. All right. We're kind of running out of time here. What I wanted to do with that little session there was just to make sure you see the questions, and because this chapter 3, this is one of the tougher chapters in the book. In fact, frankly, I think it is the toughest chapter in the book. There's a lot of meat in it. And this is why we make Jerry do it. And so
yeah.
anyhow,
Now,
um,
unfortunately, I'm not going to be here next week. I'll be doing some license exams, and have to see whether or not I'm available the week after. Let's see, that would be October the yeah. I'll be available for on the 8th. So any questions come up, we can tackle that.
okay. Um, anyhow, yeah, Those are the kind of questions that could be on your test. And so, like Jerry's been stressing, for the last couple of weeks is, get out and take those practice exams, because the more you see the same questions and see what the right answers are, after a while it settles into you. I was, I'm not a real technical guy, and I was just by doing exam after exam, practice exam after practice exam, I was able to pass the extra license exam a couple of years ago. So um, that's about it. So that's really, I think, it for tonight, and I think we can close off tonight's session. Um, Jerry, any closing words?
Ooh, it's kind of an exhausting thing because we're doing this, trying to push so much in so little time into your ears. So as I say, keep taking the exams. Uh, they're an investment that you might want to make. It's somewhere between $50 and $75 nowadays. It's the Radio Amateur's Handbook that's published by the ARRL. Comes in two versions. One I think is a thick 1,000-page book, and the other is they divide it up into smaller booklets. But it has everything that current technology has with ham radio. So and really good explanations. I know that back in the hippie era, one of the rebels, I think he wrote a book called "Steal This Book," and had all sorts of resources for going off the grid and becoming anti-government and all that sort of stuff. And he said one book to steal from the bookstore is the Amateur Radio Handbook. So there you go.
Okay. Mike, any closing words?
I just want to reiterate again, take those practice exams. Take them, take them, take them over and over and over. I mean, it's really the best way to help you pass the test without with flying colors. Jerry had mentioned the ARRL. The one that I had always used, which I still love, is hamexam.org. Ham exam is all one word. There's no sign up for this one. You just put in an email address, and it keeps track of everything you've done. It weights answers, which I think ARRL also does. If you answer something wrong, it's going to give it to you sooner than if you're answering something right. It may not ask you that as often. And so either one's good. But some people I know, I have a friend of mine who's like, oh, I'm not putting all my name and address and all that malarkey in to do that. No. And I think the ARL one wants you to actually, sign in to their site to do it. I don't think there's a cost at all to do the exams. Um, like if you're going to become a member of ARL, you don't have to be a member, but the exam itself, you got to fill some stuff out and, identify yourself. The hamexam.org, all you need to do is put in your email address. Just another one. There's about 50 of them out there probably. But those two I think we've had a lot of success with. But take them, do them, start them now. Don't wait till the end of class. Don't, start them now. What I did is I took one in the morning before work and one after work before I went to bed every day. And by the time class ended, I was getting 95 and 100% on every time I took the exams. And that's what I got when I took the test, too. So,
Yeah.
All right,
I was there.
gentlemen. Next week I'll be talking about radio wave propagation and antennas. Thanks very much.
Okay, so I'm stopping recording.